I would like to introduce our next speaker here. So hello Torsten first. It is a great pleasure to introduce our next speaker, Torsten Sattler. Torsten currently holds a position at the Czech Institute of Informatics in the city of Prague. So previously, he held a professor position at Chalmers University and spent a long time at ETH Zurich in Switzerland. So he is well known for his contributions to visual localization. Also, his expertise extends to outside this area as well. And he's also one of the people involved in the visual localization benchmark. And because of these contributions, we are very happy to have him here as a keynote speaker. So Torsten, we're very glad to have you here, and we are looking forward to your talk.
Friedrich, thank you very much for the nice introductions. Thank you very much for the invitation. I mean, I looked at the lineup of speakers, and there's a lot of people that I admire and where I'm a big fan of the research, and it's a great opportunity for me to talk in between those people. Okay, so today I'm going to talk about visual localization. And typically I talk about some algorithms for visual localization, how to solve this problem. Today I'm going to talk about two things, more application-oriented and about privacy and visual localization. But before I go into details, let's start with a definition of what I mean by visual localization. The idea is that we're given some image and we have some 3D scene representation, and we would like to compute the exact position and orientation from which this new query image was taken. This has a couple of applications. One of them is robotics. So this is a project that I was involved in when I was at ETH as a postdoc. The idea was to build a gardening robot that can cut roses and trim hedges. And in order to do its task, it needs to know where it is in the garden so that it can navigate to its target locations and then perform its operations. And this is done by using a set of cameras and figuring out where the robot is within a pre-built map of that garden. Another application area is augmented reality. So on the left, you see an example from a paper that I was involved in where we display virtual objects into the field of the user. On the right, you can see a screen grab of Google's AR navigation feature, which they launched, I think, last year. And in both cases, we try to figure out where we are in the world and then try to, once we know this, we can augment the view of the user by projecting virtual objects into his field of view. Last application is virtual reality. So this is like the result of a master's thesis that I co-supervised at ETH, where the student built this virtual map, which is essentially a Minecraft-like world of the real world. And because this virtual map is like we can physically traverse the space, which is nice. It's like some form of interaction between the virtual and the physical world, but it's very limited. So you can't really interact. And this comes from the fact that we're essentially just using a head-mounted camera here to figure out where the user is. And that itself is not really enough to capture higher level interaction of a user with a scene. And that brings me to the first paper that first work that I want to talk about. We call it Human Positioning System. It's about figuring out where a human is in a scene and also estimating the pose of the human together with this position. This is joint work with Vladimir Gultsov and Ayman Mir and Gerard Ponsmall from the University of Tübingen and the Max Planck Institute of Informatics. And Vladimir and Ayman share first authorship on this one. This will also be presented at CVPR. So the setup is similar to what we had before in this virtual reality example. We have a pre-built map of the scene. So here, in this case, we used laser scanners to build like a dense 3D model. And we have a human. What's the same as before is that we have some head-mounted camera, which we use to figure out where the human is in the scene. What's new is that we are actually using a set of IMUs mounted on the body of the human. And those are used to estimate the human pose. And here's like a first prototype where we essentially use the IMUs on the body of the human to track the body motion and the camera to figure out where the human is in the scene. And it works kind of, but there's a lot of, this is clearly not a realistic smooth motion. What happens is that there are localization failures and inaccuracies that lead to those jumps, to the human flying in the air. Part of this is easy to fix, so you could just filter out camera pose estimates that are jumping too far away from frame to frame, just using some sort of temporal consistency. But there's still jitter and still some small inaccuracies, so you'll see the person walking slightly above the ground, then in the ground, and so on and so on. So this is not really realistic. And the idea of this human positioning system, or HPS for short, is that we're not going to only use the head-mounted camera and the IMU, but we also want to use some information about the 3D scene, and then jointly use all this information to get the human pose in the scene registered with respect to that map. So let's briefly talk about this. What we do is we optimize over the body pose parameters, and I'm not going to go into detail. For those who are interested, it's a simple model proposed by Lopper et al. In 2015. I think there was actually a CVPR tutorial on this human body parameterization. We initialize the pose of the body, which is essentially a set of joints, and the position of the body in the world based on the IMU, which is used for the body pose, and the visual localization results for the position or translation. And then we optimize an energy function over like small batches of frames. And most of these terms are rather standard. So the first term essentially says that the body pose should be consistent with the estimated camera poses. And we have a weighting term W log that is applied to that term. The second one is an IMU term, which essentially says the body pose that we estimate should be consistent with the IMU measurements that we get. And then we have a smoothness term, which essentially says we don't want to have large jumps, so that avoids having like unrealistic motion. The interesting part is, I think, the scene constraints. And in this work, we use a very simple one in order to avoid that the human is either can walk through the ground or above the ground. But you could also add more complex ones. And the way that this is done is we use Xsense IMUs, which give us body pose. It gives us some idea of how the body moves in 3D space. But it also gives us information about whether one of the feet or which foot is currently touching the ground. And what we did is we manually labeled vertices on the feet corresponding to the toes and the heels. And then we essentially, for the foot that's touching the ground, we essentially try to minimize the difference between like the vertex position of the toe or the heel and the ground. And that's a very simple way of adding like a very simple scene constraint, but it essentially avoids that the human is doing this bobbing motion, walking in and out of the floor. So here's the result. These two I already showed you before. This is our joint optimization without scene constraints, and this is the optimization with scene constraints. And as you can see, the full approach is clearly like the smoothest, most realistic one. Okay, and let's look at some qualitative results. So this is one sequence of a human walking through the Max Planck Institute or around the Max Planck Institute in Saarbrücken. And this is just the pose that you see is just computed using the IMU sensors and the head-mounted camera. There are no external cameras that are used to track the human motion, which actually allows us to scale to arbitrary scenes as long as we can pre-scan them, because there's no need to mount a set of external sensors, calibrate them, and so on and so on. And since we are estimating the human pose from sensors mounted on the body, we can naturally handle like multiple people. So here you see two people playing with a basketball. Both of them have the sensor set up, and then the poses are estimated independently of each other. Here you can see two persons carrying a package, and while it's not perfect, you get a good idea of what those people are doing. As with any more complex systems, there are of course limitations. So I told you about this very simple scene constraint, which essentially prevents the human from flying in the air or walking through the ground. Since this only applies to the feet, we are a bit in trouble if the person is sitting. So this, what you see here, happens because the localization system is not one, like doesn't give you an accurate pose, but jitters slightly around, and then you see this type of thing happen. But I think this can be relatively easily fixed by adding additional constraints into the formulation. Here's, from my perspective, more interesting example where the human actually seems to be walking through some table. But what happens is that the table was there when we scanned the scene, but it was not there anymore when we were actually capturing the motion. And I think this looks trivial or it looks simple, but essentially this is an important thing, because if you want to have more complex scene constraints, so preventing the human from walking through pillars or walls or touching the like having a leg or so in them, then you actually need to account for changes in the scene. And then that itself is not a trivial problem to solve. But yeah, to summarize, so here what I showed is one application of a visual localization system that is able to localize a camera in space. And by combining this with a pre-scan model and IMUs mounted on a human body, we can actually capture quite realistic human motions in large arbitrarily scaled scenes. And I think the results are, when I first saw them, I was very impressed by the quality of the motion. It's super smooth. And I think there's a lot of interesting applications for this type of technique. So one is some form of interactive VR, similar to the simple example that I showed. But now you actually you can try to reason about what the human is doing in the scene, and that you could, in this way, you could have interaction with the virtual world. So for example, here you see a human taking out a book. In a virtual world, this could be like opening a portal or something. Obviously, the same technique is also applicable to humanoid robots, where you could localize and then reason about the body pose. We're going to present this in session 4. So if you have any questions, you can ask after the talk or during the talk, or come and visit us at our poster. And we're going to make the data sets and the code publicly available. Yeah, are there any questions now before I switch to the next topic?
Well, actually, there is already a question, and maybe I can read this question right now.
Yeah.
So the question reads, so with the IMU consistency term, does it mean it should be restricted to very accurate IMU? What if there are quite a lot of accumulation errors of IMU after a long time running?
Yeah.
Or if you have low quality IMUs, I think.
So that's a good question. What it means is that the IMUs give you like relative poses, so to speak. That's how we use them. We're not accumulating the whole thing over the full sequence, but we're looking at short sequences where IMUs are actually not drifting that much. But you could, since the visual localization system gives you a global pose that is actually not subject to drift because you're localizing within an existing map, you could actually prevent the position drift that you have from IMUs by having this. Essentially, if you think of this in terms of a SLAM system, then what localization does, it gives you a sequence of loop closures with respect to previously visited scenes. I hope that answers the question.
Okay, thank you.
Good. So the second part looks a bit more into localization techniques, and I'm mostly going to focus about structure-based localization. What this means is that we assume that we have some 3D model of the scene. That can be either a set of explicit 3D points or a mesh, or it could be represented, or the 3D geometry could be represented implicitly through the weights of a neural network, for example, scene coordinate regressor, or any other type of implicit neural representation. And then given like a test image, what we want to do is we want to establish correspondences between pixels in the image and 3D points, like points in the scene, the 3D geometry. And once we have those 2D, 3D matches, we can do pose estimation using classical algorithms, minimal solvers on the perspective endpoint pose problem. And so this is how a lot of state-of-the-art localization techniques work at the moment. And those things are also being deployed in practice by companies. Then there's this thing called the AR cloud. I guess many of you have heard about it. The idea is that there's a cloud-based service where people can send images, video streams, and this service will run visual localization and give them a camera pose, and then potentially also directly do augmentation in the images in the form of augmented or mixed reality. And that requires that you have to have some sort of 3D maps stored in this cloud. And that's not a problem if you think of like self-driving cars, where all like the maps are actually public knowledge. It captures scenes that are publicly accessible. What's more interesting is what happens if you actually ask users to upload like 3D models of their homes or private spaces. How can you ensure that if a user trusts you with data, that no one can recover privacy relevant details from these 3D maps? There was a very nice paper at CVPR 2019, which essentially showed that like this classical scene representation of structure-based methods, which is essentially structure for motion point cloud, where you have a set of 3D points and each point has an associated descriptor. This representation, even though it's a very sparse point cloud, that's not privacy preserving, because you can train a neural network that takes the projection of the point cloud as an input and then recovers a nearly photorealistic image. So here you see the results of the recovery process. This is the original image, and this is just recovered from a sparse point cloud. And the way this works is you have the input images like a tensor, which takes the projections of 3D points as input, the depths of the 3D points, potentially color, and a SIFT or another descriptor. There's one subnetwork that figures out which of these points are actually likely to be visible and which are likely to be occluded. And then this visibility information is used to first recover like a coarse outline of the image and then to recover fine details. And then there was a second paper, one at CVPR, which essentially said, okay, point clouds are not privacy preserved because I can project my points into images. or like into viewpoints and then recover images. Let's try to make sure that we can't actually do a meaningful projection by essentially lifting each 3D point to a line with some random direction that passes through this point. And this is the result. And to human, this is nonsense. It's not, you don't see anything in there. But so this directly prevents this inversion process because you can't project 3 points into images anymore. But the question is, can you actually recover 3 points from those lines? And this is a second paper that I want to talk about. This is joint work with Kunal Shilani, the first author of the paper, and Frederick Kahl from Chalmers University. So let's quickly look into a bit of technicalities. So what this privacy preserve, this approach that I showed before does is it takes a 3D point, it randomly chooses a line direction uniformly at random from the unit sphere, and then throws away the original 3D point. So you essentially add 1 degree of freedom, meaning the point can be anywhere on this line. And if you only look at the single line, this is perfectly privacy preserved because you have no idea where the 3D point is. The problem is we have actually many lines, and this gives you information about the scene structure. So let's look at the case of two lines, and this only makes sense in 3D. So these are 2 3D lines. This is meant to be the shadow of the pink line. Because the whole technique that I'm going to present is not going to work in 2D. So if you have 2 lines, you can compute the closest distance between the lines, and you can look at the closest point to the line. And what we observed is that if you choose those line directions uniformly at random, then there's actually a good chance that this closest point to the other line is reasonably close to your original 3D point. So this is visualized here. You have 2 3D points, and we randomly selected lines for each of them. And then those bright pink, small white dots are the closest point on the line corresponding to the white point. That is the point that's closest to the other line. You see that they actually cluster around the original 3D point. So there's actually some signal that we can use to recover the 3D scene geometry. One thing to observe, though, is that if you denote the distance between the original 3D points by d1 and the distance between one point and the closest point on the line to the other line, if that's d2, then you actually see that the ratio of the distances is likely to be smaller than 1. And what this implies is that you actually get better estimates for the original pink 3D point if you can identify lines that correspond to nearest neighbors of the original 3D point. The question is, how do you actually get these neighborhoods? Because we have lines, we don't have those 3D points. And we end up doing this iteratively. We start with a line cloud. We estimate nearest neighbors between lines by essentially figuring out which lines have the smallest distance. And that gives us like an initial set of neighborhoods. We estimate 3 points. So for each, say we want to estimate the 3 point for this green line. From the neighboring lines, we get candidates on where the 3 points could be. And then we do some density estimate, density-based estimation. I'm not going to go into details. So this gives us a core set of 3 points. And then we can try to find a better neighborhood, because now we actually have lines and 3D points, and we can find nearest neighbors based on lines and points. That typically gives us a better estimate of the true neighborhood. We can re-estimate the 3D points, and we can iterate a couple of times, and then typically get a much cleaner result. Here are some results. This is the original point cloud, and you see 2 images recovered from that point cloud using this inversion scheme that I showed before. And this is the point cloud that we recover from using our algorithm from a line cloud. You see it's much more noisy. And this is actually already cleaned up point cloud. We filter out some gross outliers. But still, it's good enough that if you render 3D points, the render images using that point cloud and color and descriptors, that you can, it's to human meaningful what you see in those images. Here's an example for an indoor scene. This is the original point cloud, images recovered from the original point cloud, as well as the point cloud that we get with our algorithm. And you can clearly see that while the images are much more noisy, you still see that there are shoes here, there's a bed here. So essentially what we've shown is that line clouds themselves are not automatically privacy preserved. But actually, I believe that you can make them privacy preserving. So one thing that there are two things that our algorithm relies on. So one thing is we need to have like a good estimate of the neighborhood of the original 3 point cloud neighborhood, because close by points give us good candidates for recovering 3D points. And one way to make it harder to get good 3D points estimate is to actually introduce sparsity in the whole thing. So rather than using all 3 lines that we have, we could only store a subset of them. And this is what you see. This is what happens if you take 50% of the original lines, then you get something where you can understand, where human understands what's in the scene. But as soon as you get to like 5% or 1%, you stop seeing what's actually, you can't recognize what's in the scene anymore. And the interesting part is that localization with line clouds is actually still possible at this level of sparsity. What's interesting though is that even if it's even hard to recover private details, even if you just store point clouds and not line clouds, because sparsity is actually hard for the inversion process. So sparsity itself seems to be like an important property for if you want to ensure that what you store is privacy preserving. The other thing is we assume that like nearest points between lines are actually good, reasonably good approximations to the original 3D points. And this works if you choose the line direction uniformly at random. But you could think of trying to find better distributions where you pick one line direction first, and then you choose another point, and you choose a line direction so that the 2 closest points between the lines are actually far away from the original 3D points. And then you iterate this. But I don't think that it's super trivial to do this, because you still need to ensure that you can do pose estimation. And then you could potentially apply our algorithm, still apply it, get some 3D points. The human tells you whether this is meaningful or not. And then you clean up some neighborhoods and you iterate. That might work. But I think it's a very interesting direction for future work. The other way that ours can fail is that if we cannot recover neighborhoods. And there you could think of introducing, for example, like using different line direction distributions to make sure that those closest points between lines are not useful for recovering neighborhoods. Or you could try to introduce fault structures to mislead the recovery algorithm. Or you could actually try to say, I'm fine with recovering certain parts, and then make sure that lines get falsely, or points get falsely recovered in those parts and not in the rest of the scene. So what I hope I convinced you about is that privacy-preserving localization is a very interesting young subfield, and there's a lot of open research to be done. One of the chief things is to actually define what constitutes privacy and what one would be allowed to recover from a scene, and what is not should not be recoverable. And then I think there are interesting questions about whether we can actually prove privacy preservation under certain conditions. As I said, this is a CVPR paper. We're going to present it in the last session, and we actually have code available online. And with that, I'm nearly done. A bit of self-advertisement. We are going to have 2 more papers at CVPR this year. The first is with Kunji Zhu and Laura Leal-Tager, which will be presented in session 4, and which is about establishing correspondences between images on a pixel level. The second is with Paul Eduard Sarlin and AJ Unaga and many others on doing localization without actually having explicit correspondences between 2D points and 2D pixels and 3D points, but rather having some sort of photometric refinement. And I'm actually sure that Daniel Kremers might talk about something in that direction in his talk. So what I skipped today was actually how localization algorithms work in detail. If you want to know more about this, we're going to give a tutorial on visual localization at ICV, and we're also going to have a workshop with challenges on that topic. With that, thank you very much for listening, and I'm happy to answer any and all questions.
Thank you very much for this nice presentation. We now have time for questions. So if you have some questions, please type them into the chat, and then I can read them to Torsten. Maybe I can already start with a question. So in the last part, you mentioned the inversion process. So to train this inversion process, does one need actually the corresponding image data and the 3D data, or can you train this only from the SIFT features and descriptors only?
So for training, I think you need the images because you need to have a loss function, right? But for the input, I mean, the images are only needed to compute the loss because you want to compare the pixels that you recover with the pixels that you're supposed to recover. At test time, you only need 3D points. And actually, so you can do without color and you can do without descriptors. You'll probably get better results with them, but like a color point cloud or just depth values themselves can also already give you something meaningful. One thing that I should mention for all these inversion results, such as those, we actually never retrain the network that recovers images. So this is the result of a inversion network trained on structural motion point clouds, but much less noisy ones than ours. You could potentially get better results if you train the network on more noisy point clouds.
Sure. Okay, thank you. I do not see a new question in the chat. Guyu, is this a question somewhere else?
I think it's easier for me to ask directly in this case.
Yes.
Yeah. So Torsten, and thank you very much for your talk. And I have a follow-up question. And in the privacy preserving localization, so I can see there are quite a lot of straight lines in these scenarios. What if they are not? In some scenarios, in some scenes or situations, there are not many straight lines. In those situations, is it restricted that only key points can be applicable for localization?
I'm not sure if I understand the question, because so what happens is you start with a point cloud and then you replace each point by a line, and that is not that does not depend on whether you actually have planar structures or line-like structures in the original scene. If that was the question.
Okay. Okay.
But so what is actually, I think, interesting is that you could potentially go from lines to curves. That will probably make the pose estimation problem a bit harder on the localization side, but would probably also make it safer because you have much more freedom for fitting those curves, and you could try to introduce like misleading structures where curves are close by, and so on and so on.
Okay, and also, so in epipolar geometry, the epipole and epipolar line are actually one-to-one mapping. Have you ever considered about applying for the epipoles instead of using the pair line to find their shortest distances? Those kind of geometry to find the line to convert from the point to the line.
So this line-based localization technically works in this way. So if you want to localize an image with respect to a line cloud, then you get 2D pixels to 3D line correspondences. And you could think of those line correspondences as defining a generalized camera. So you're resulting in the problem of estimating the pose of a perspective camera with respect to the pose of a generalized camera, so a camera with multiple centers of projection. If all of those lines would meet in a center of projection, then you would actually end up with the relative pose between a perspective and a perspective camera, and then localization doesn't work because you don't get the scale of the translation. So in this sense, there are actually no epipoles in these line clouds. So what you see here in this projection, this is essentially taking each 3D point, fitting a line, like having some 3D line going through this, and then you project this. There's really no epipolar geometry involved in this.
Okay. Yeah, thank you.
Okay, I have one more question here for you. So you also in the beginning, you mentioned an AR cloud for localizing the images for augmented reality. So the question would be, so when do you think we will have such a well-working AR cloud, which works very well and reliably?
Can you define what you mean by well-working reliably?
Well, that it works on a city scale and precisely enough with such that you can really overlay precise information, and it works, reliably. So on all the places that you can think of in a city.
I mean, if you look at this Google example, this is essentially an AR cloud, no? And this works reasonably reliable. So I tested it out a year ago and it worked very well. Back then, and I haven't checked in a while, when you try to do this at night, it told you this is not going to work at night. And I think there is still, so we see the infrastructure for this AR cloud. We see it at Google, like this Google Map AR navigation feature. Microsoft has Azure spatial anchors. If you look at some of the work that Facebook announced, then I'm sure that they have something like this. I'm pretty sure that Apple is building up something like this. So I think that it's like having the infrastructure up and being able to upload images. I think this is essentially there. The question is, how do you make this like work under all conditions all year long? I think that's still a research question. How long this will take, I don't know. When we released this visual localization.net benchmark, where we had changing conditions, I thought we're not going to make any progress there anytime soon because it seemed like a hard problem. 3 years later, most of the data sets that we released are close to being solved. So maybe a couple of years, who knows? I think we're getting there where this will become like readily available at scale, at least at big companies.
Okay, thank you very much for sharing your opinion on this. I think I do not see any further question here. So I would like to thank you again for your nice presentation. It was good to have you here.
Thank you very much for the invitation. It was my pleasure.